Happy morning, everyone, and welcome to the IBM Qiskit Live Quantum Seminar, dedicated to you, the research and academic quantum communities. Now, in just a minute, I will be delighted to roll out this week's episode with Dr. Patrick Rall from none other than IBM Quantum, my very own colleague and friend. Before we get there, I'm so glad you joined us on time because we have a tradition. And that tradition is to check in with you and ask you, where are you guys tuning in from today? That is my favorite question on episode 144, I think for the last 144 episodes, because it just helps us show what kind of a global community we have and how we're all coming together around this purpose of bringing useful quantum computing to the world. Now, if you want to know more about that purpose and how that progress is going, go back to last week's episode where we had Dr. Jay Gambetta from IBM Quantum and 4 other panelists looking at the state of the field and a significant change going from small scale to 100 plus experiments. It was a really fun episode. We had sort of 200 people live plus concurrently with a lot of discussion in the chat, which kept me very busy. So take a look at that. That was a great episode. I see Kevin is here from last week as well. So some of you might already be very familiar. Now, before we get to Patrick, let me just remind you that you can ask questions live during the seminar anytime, and I'll try to bring those up to Patrick at convenient moments in time. We also have a new seminar, a new series, a paradox series with Maria on the channel coming out, which will throw you into the mysteries of quantum. Now, this seminar takes place every Friday at noon Eastern Time right here on the Qiskit YouTube channel. So to know what's coming up, click like and subscribe. And today, let's dive right into it. I'm your host, Zlatko Minev from IBM Quantum. And on this episode 144, I have the delight and pleasure and privilege to introduce you to Dr. Patrick Rall from IBM Quantum. And hello, Patrick. How are you today?
Hi, good morning. I'm doing well.
Now, you noticed something very interesting to me before we started. Why 144 is such a special number to both you and this panel here, the seminar. And I think I'd like to share that with folks that Patrick is going to talk about a 144 qubit code. So we couldn't help ourselves but pick this specially for you, Patrick. So it's our pleasure to have you here. Mm-hmm. Now, folks, allow me to introduce Patrick briefly to you. Patrick is a research staff member at IBM Quantum. Patrick received his bachelor in physics at Caltech and his PhD in physics at the University of Texas at Austin. Patrick's hope and ambition and what keeps him up at night and keeps him up at day is to make useful fault-tolerant quantum computation a practical reality by developing useful quantum algorithms for large-scale problems and efficient error-corrected quantum architectures, which is what we'll hear about today. So with that, Patrick, the stage is yours.
Thank you so much for the introduction, Zlatko. So, on that second point, I think a big research goal that I have and many of my colleagues at IBM share is making fault-tolerant quantum computation something practical and something real. And in order to get us there, we're going to need quantum error correction codes that can really support the foundation of fault-tolerant quantum computation going forward. So in particular, we'd need a family of error correction codes that we can actually realize in hardware. My co-authors and I were interested in the following sorts of research questions. What kind of quantum error correction codes could make for early fault tolerance experiments, small codes that we can actually try to build and see how well they work? And if they work well, could form the foundation for a IBM quantum computing architecture with tens of thousands of physical qubits in it. And in particular, we'd like to do better than surface codes. Surface codes are sort of the state-of-the-art quantum architecture right now. If you look into the literature and see the ways that we usually benchmark our future fault-tolerant quantum computers, they're usually all done in terms of surface codes. And I think that's for a good reason. Surface codes have very many nice properties. They have a high noise threshold. You can scale how much error protection you get very nicely. Their gate set is well understood. However, they have one big drawback, and that is that their encoding rate is somewhat poor. So that's the number of logical qubits per physical qubit. The amount of overhead that you get in terms of qubit count for using error correction is pretty enormous with surface codes, and we would really like to do better. Fortunately, there's been a lot of progress in the field of quantum error correction, in particular recently, studying these low-density parity check, or LDPC codes. So what these codes are quantum error correction codes where each parity check, each check to make sure that the quantum bits are in the correct state, doesn't involve too many qubits. So that makes them sort of feasible to realize in hardware. Technically speaking, surface codes are a kind of low-density parity check code. So when we say low-density parity check code, what we really mean are codes that violate some of the assumptions that go into the construction of the surface code. Surface codes live on a surface, as the name says. You have a bunch of qubits that are on a sheet, and they're all coupled next to each other. You don't have any long-range wires. You don't have any wires that cross, none of that. And with LDPC codes, we're explicitly allowing these sorts of things now and asking, well, how much better can you do when you're no longer restricted in this way? And it turns out that the answer is you can do a lot better. Recently, there have been discovered very high performance families of low-density parity check codes. And what we're curious about now is, rather than such large infinite families of LDPC codes, can we find a small practical example that we can build using order of a couple hundred qubits? So let's go through a wish list, shall we? What should that quantum error correction code look like? What should its properties be? So in particular, we would like an error correction code with a large distance and encoding rate. So the distance is a way of measuring how much protection we get, how resilient are our logical bits to the errors of the device. We want that protection to be large enough. And also, while doing that, we want to cram as many logical qubits into there as possible. The second thing we would like is a high pseudo threshold. So what is a pseudo threshold? Quantum error correction involves a fair amount of machinery. It involves, first of all, using many more qubits physically than you're actually storing. You're constantly checking if those physical qubits are in the correct state, and you're just running a circuit that's verifying that over and over again. There's a lot of overhead associated with that. And there is a point at which that overhead starts to break even, like a point at which the amount of protection that you're getting from all of this machinery starts to actually outperform what you would have when you would just run the circuit directly on the hardware. And that's what the pseudo threshold is. We want that to be high enough that our hardware noise can go below it. So this is in fact a property that the surface code has. It has this high pseudo threshold, and we would like this property as well. Now, I mentioned that surface codes had this very nice property that they were implementable on a flat sheet, that you could have all the qubits sort of coupling only when they're close to one another. And furthermore, none of the wires can cross. And we were going to consider lifting some of these restrictions. However, ideally, we would like to only lift them a little bit. It would be nice, rather than saying, well, we just allow arbitrary connectivity graphs now, we consider connectivity graphs that are still somewhat implementable. And maybe the easiest thing that you can build that isn't just one sheet of qubits is two sheets of qubits. You have one sheet where the coupling graph has no crossings, and then on the other sheet you have another coupling graph that has no crossings, and then you have couplings in between the two sheets. So this gives us access to certain types of connectivity graphs that would not be implementable on just a single sheet, because then you would have crossings. So another thing we would really like is a short syndrome measurement circuit. A syndrome measurement circuit is really the beating heart of quantum error correction. When you do quantum error correction, you're constantly measuring, are the qubits still okay? Are there any errors? Over and over and over again. And when you do notice any errors, you go in and fix them. So not only is it important that that circuit is fast, because the longer the circuit is, the more errors could accumulate within that circuit. But then the other reason is that it sort of sets the clock rate for your quantum computer. The faster the syndrome measurement circuit runs, the faster you can run the underlying clock of that quantum computer. So we'd really like this circuit to be short and efficient. And then finally, what's the use of having protected quantum bits when you can't do anything to them, when they're sort of buried away in this error correction code that's protecting them from the noise, but also protecting them from you and your desire to manipulate them to perform computation? So we would like some family of fault-tolerant logical gates, operations we can perform on the bits without damaging them, or at the very least load store operations, such that we can use this code as a memory, load data in and out. So this is essentially our wish list. These are the things that we would want out of such an error correction code. And for the rest of the talk, I'm essentially just going to go through this wish list and show that the family of codes that we found seems to satisfy these desired properties. So without further ado, let's take a look at this family of error correction codes. So this is a family of CSS codes that were first studied by Kovalov and Priatko back in 2013. So the family itself is not quite new. However, the examples that we found and some of the mathematical treatment in our work is new. So these are CSS codes. And what this means is that rather than using arbitrary Pauli matrices to check whether or not our qubits are in the correct state, we're going to focus entirely on either completely X checks or Z checks. So all of our Pauli matrices are just strings of X's or strings of Z's. And that makes it very easy to define such a code in terms of a so-called parity check matrix. So this is a matrix that consists just of zeros and ones. And each row of this matrix corresponds to a certain check. And each column of this matrix corresponds to a physical qubit. So if we have a certain row within this matrix here, that row has a bunch of positions with ones, and those positions indicate what physical qubits participate in that particular X check. So we're just considering X, 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 X on those particular physical qubits. Now, we want these measurements to be compatible with one another. In the sense that all of the X check measurements commute with all of the Z check measurements. Now, you can see in the way that I've defined these codes in terms of these matrices A and B, that's done for a reason, and that's because if A and B commute, if the matrices A and B commute, then this form actually guarantees that the X checks and the Z checks are compatible with one another. So all that remains essentially is to specify what these matrices A and B are, in a manner that guarantees that they commute with one another. So this is where essentially the bivariate bicycle comes in. We're going to be defining these matrices A and B through a bunch of permutations. And these permutations are going to be a representation of a kind of bicycle group, a group with two cycles in it. So in particular, we're going to be choosing two size parameters, L and M. And these are going to define a matrix group that's congruent to ZL by ZM. So just integers modulo L, integers modulo M. One way of thinking about this group is via a torus. And that torus has a grid on it. And we're considering rotations around one axis of the torus that has L grid elements, and then rotations around the other axis of the torus that has M grid elements. And the group that we're considering is just the set of translations within this grid on a torus. This grid has a matrix representation. This group has a matrix representation. So one way you could represent just ZL on its own is via a permutation matrix like this. So this is a matrix with just 1, 1 in every row and every column. And it just takes the ith element to I plus 1. So if you see, you can just take powers of this matrix to get everything in this ZL group. And to get this bicycle group with the two cycles going on, I'm going to consider a tensor product of this permutation matrix on one side, identity on the other, or an identity on the group of order of L and just the generating element for the group of order M on the other side. So that gives us these generating matrices X and Y. They are of size LM by LM. And they're going to lay the foundation for these matrices A and B because just by construction, they commute. This group ZL by ZM is an abelian group. Every element in that group commutes, so therefore do their matrix representations.
And maybe before I let you get too far, Patrick, this is great. Thank you for walking us through it very carefully and slowly, because we haven't had a quantum error correction seminar in a while. Let's see if maybe I can briefly try to summarize for us. So you're going to use only your parity check matrices. The observables you want to be in some state are going to be only either X based or Z based. And you have two sets of these. And then the HX matrix, if you want, is its rows, of which it has L rows, like 12, for example. Those are, is that right? Yeah, that's 12 different parity checks, which correspond to 12 different X polys, basically. And kind of the columns tell you the number of the qubit indices. And these are just Z2 matrices over 0 and 1s. So far, so good.
Yeah, that's very close to being right. So these matrices, A and B, they're going to be formed from sums of powers of X and Y. And as I said, these matrices are LM by LM. So in our case, 12 by 6 is 72. So we have 72 many checks of each kind. And the number of physical qubits would be 72 times 2, because we have 2 of these blocks, giving us 144 total. Now you could choose other values for L and M. So in general, you have L times M many checks of each kind, and then 2 times L times N many qubits.
Got it. And the elements or entries of A and B are over which field?
Over GF2. So they're zeros and ones.
Zeros and ones. Okay.
And they just indicate, does this qubit participate in this check? Yes or no?
Got it. And maybe you'll mention this for us soon, but yeah, these remind us a lot of Pauli check vectors, or also the Heisenberg-Weil operator. Kind of the SL looks a lot like that. Maybe I don't know if you want to mention that now or later.
I guess you could draw an analogy between these permutations and the Weil group. I don't think we found that connection particularly useful for this talk in particular, for this work in particular.
Okay, thank you.
Perhaps let's go on to define the matrices A and B. So we're going to take some elements of this group and add them together. In particular, we're going to take 3 for each of them. So what you can see from this construction immediately is that this is a low density code. So let's, by low density, I mean the number of qubits that participate in each particular check is 6. Why is that true? Well, each permutation matrix has exactly 1 1 per row. And this matrix is a sum of 3 of them. So it's going to have per row 3 1s. Similar for the matrix B. So if we look at each row here, we're going to have 1, 2, 3, 4, 5, 6 ones per row. So number of qubits participating in each check. So that's one thing you can see. Another thing you can see is that these are permutations. So that means that are permutations that are elements of this abelian group. So therefore, these check matrices are compatible with one another. So this broadly is sort of the framework that we're going to be using to constructing our error correction codes. Here I give one example, this 144 qubit code, very aptly chosen for episode 144. But we actually have a bunch more. So this was a supercomputer search where we looked over a bunch of different parameters, L and M. We had some restrictions in terms of what polynomials we would choose. For example, we wanted the checks to be weight 6. And we filtered these codes for codes with particularly high encoding rates. So the encoding rates is just the number of logical qubits divided by the number of physical qubits. And what you can immediately see is that we have these really high quality encoding rates, especially compared to the surface code. Surface codes, so we more or less have a factor of 10 improvement in terms of encoding rate relative to the surface code. And that would be for a code with a very similar distance. So let's look at the error correction properties in a little bit more detail. This is sort of a very standard plot that maybe most research papers on quantum error correction should have, especially if they're proposing a code. On the x-axis, we have the physical error rate. So that's the rate at which errors creep into the hardware. And then on the y-axis, we have the logical error rate that the actual logical qubits experience. So going from here to here essentially shows you how much protection you get. We went from an error rate of 10 to the minus 3 to an error rate of order of 10 to the minus 7, which is a pretty significant improvement. And here we are comparing the 144 qubit code to a bunch of similar surface codes. Now, ideally, we would compare to a distance 13 surface code. No such surface code exists. They only have odd distances. So we took a couple here that have similar distances and the same number of logical qubits. And we find that the rate of protection is roughly the same between the 144 qubit code and the surface codes. However, the number of physical qubits is an order of magnitude better, like a factor of 10 better than the surface codes. And I think this is the main reason why I am so excited about these error correction codes, is that they let you get access to these high quality properties of the surface code using just way fewer resources. One thing that you can't see on this plot is the pseudo threshold. So if we were to continue this plot further to the right, there would be a point where you would no longer see this improvement. And the point in which that improvement starts happens at around 0.8%. So the threshold of the surface code is at around 1%. So we can see that we're doing roughly the same as surface codes in that sense as well.
Question from Siddhant. Can you remind us what the noise model is at the level here of this discussion?
Yeah, that's an excellent question. So for this plot, we were interested in circuit level noise. Circuit level noise is probably a better representation of the kind of noise that we're actually going to see in the hardware. Of course, there's a lot of papers out there that consider, say, just depolarizing noise because it's an easier calculation. But here we wanted to look at circuit level noise.
Can you tell us what that means?
So you have a quantum circuit, and after each CNOT gate or single qubit gate, there's some probability of a poly error occurring, and that probability is P.
Great. Okay, thank you. Good. Siddhant, hopefully that answers. Folks, feel free to post questions. We always love to have a discussion. Thank you for the good questions. Carry on, Patrick.
Okay. So let's go back to our wish list. Just from what I've shown you so far, I think we've earned the ability to check off the first 2 points. We've showed how we have a large distance and encoding rate, an encoding rate that's significantly better than that of the surface code. And we have a pseudo threshold that is about as high as that of the surface code in the circuit noise model. So in terms of having many qubits and being easy and protecting those qubits well, we're doing very well. Now let's talk about how we might actually build such a code in a bilayer architecture. So that is showing that the ways that the qubits need to be connected to one another can actually be realized on 2 planes, each of which don't have any wires crossing. So in order to do that, we're going to need to actually draw all of the connections between the qubits. And that is visualized very nicely by a graph called the Tanner graph. Our goal will essentially be to construct a visualization of this Tanner graph. So let's do a quick introduction to Tanner graphs. Tanner graphs are just a very convenient way of visualizing quantum error correction codes. So here, for example, is the Tanner graph of the surface code. It has 3 types of vertices, at least for CSS codes. We have one type of vertex, which is just data, like physical qubits occur as data vertices in this Tanner graph. And then we have 2 types of check vertices. So for example, in a surface code, we would demand that these 4 qubits, 1, 2, 3, 4, are stabilized by z, 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 z. And the way that this is visualized is by having this z vertex here that connects to all 4 of them. So what's very nice about this is that you can just see exactly the structure of your code at a glance. But it also is very nice because it tells you exactly what you need to build, at least from the purpose of superconducting hardware. If your goal was to actually execute this z measurement here, you would need to initialize this qubit in the 0 state, or in the plus state rather, perform a bunch of CNOTs, and then measure this qubit again. So you actually do need to physically build this qubit in order to realize this code. So that's, of course, the reason why we're interested in constructing the Tanner graph. If we can show that the Tanner graph divides nicely into 2 sheets, each part of which is planar, then we've achieved what we wanted. We've shown that we can build this in a bilayer architecture. So let's try to wrap our head around the Tanner graph of the bivariate bicycle codes. To do that, maybe it's first worth observing that the Tanner graph is bipartite. None of the qubits connect to one another, and none of the checks connect to one another. You only have some checks and some qubits, and those are connected with one another. More precisely, we actually have kind of a stack of two bipartite graphs. We have a bipartite graph between the x checks and the data qubits, and then another bipartite graph between the data qubits and the z checks. And what's nice about viewing things this way is that the adjacency matrices of these bipartite graphs are just the parity check matrices that we talked about earlier. So that's going to come in handy. Now let's take a look back at the parity check matrices of the bivariate bicycle code. As we saw, we constructed these by taking these two square matrices A and B, and that naturally divides the physical qubits into two categories, sort of a left data block and a right data block. And each one has equally many qubits. All of these have L times M many qubits in them. So maybe one way we might change this bipartite graph figure is to make it look like this. We've taken this middle set of qubits and split it into two categories. And now we have this chain of 4 different bipartite graphs whose adjacency matrices are given by these matrices A and B that we defined earlier. Right. So now let's try to draw something that looks like this. To do that, let's recall that the matrix A was a sum of 3 different permutations. So let's just think about an adjacency matrix of a bipartite graph that's just one permutation. That would just take pairs of qubits and connect them to one another. Now, if we add one more permutation, then we have these connected pairs of qubits, or connected pairs of vertices, and we're adding a bunch of secondary connections. And that should give us the ability to take a walk from one side to the other side, zigzagging our way across, that essentially should loop back on itself eventually, because these group elements, we live in a finite group with these permutations. We eventually need to loop back on ourselves if we do the same thing over and over. So this kind of walk might take us between X and L, X and L, X and L, and eventually we'll loop back. And we can do that for any of these pairs. So we'll take that observation as a starting point to construct a grid like this. So we're going to take, say, starting at the vertex X, at an X vertex, and then walk back and forth between XR, 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 alternatingly using different edges in B. Similarly, we can do XL, XL, XL using different edges in A, and so on, and construct a grid. And this grid eventually loops back on itself in both directions. So really what we've done is we've constructed a grid on the torus. So that's maybe one way of visualizing this Tanner graph. It's, in this sense, it looks quite similar to the toric code, in the sense that we have just a bunch of vertices, sort of a grid tiling on the torus with qubits that are nearest neighbor connected to one another. Now, we haven't covered all the edges this way. We've only used 2 of the permutations in each block. So let's try to do something that uses really all of the edges. And in particular, we're going to try to prove this bilayer property. So let's remind ourselves what that is. Let's draw a visualization. We have sort of 2 sheets, and each sheet supports a bunch of wires that are not allowed to cross. And then those wires can connect to a set of qubits that are sort of in between the 2 sheets. Graph theoretically, graphs that can be split up this way, split into 2 planar graphs, are called thickness 2. So the thickness of the graph is the minimum number of planar graphs that the graph can be decomposed into. So here we're looking for a thickness 2 decomposition of this graph. So here it is. Let's step through this carefully. So recall that the matrices A and B were a sum of these 3 different permutations, A1, A2, A3, B1, B2, B3. And our goal is to essentially cover all of these edges, show that each of the collections of edges associated with these permutations have some kind of representation within our graph. So let's start over here, where we look at edges A1, A2, B1, B2 to define this grid right here. We're going to do this walk that I described earlier, alternatingly stepping along B1, B2, B1, B2 to proceed in the X direction, and A1, A2, A1, A2 to proceed in the Y direction. So this is going to give us a code that is planar on a torus, but we want it to be planar on a plane. So we're going to need to cut somewhere. So what we're going to do is we're going to take this torus, grab a pair of scissors, and just cut it into strips. So we have a bunch of horizontal strips here. And we've severed all of the A2 edges, so we won't be able to cover these, but at least the B1, B2, and A1 edges are all going to be covered in some strip. These strips can then be unwound to make this sort of wheel structure, which is clearly planar. We don't have any wires crossing. So we've found a way to cover edges B1, B2, and A1 using just one planar graph. Now we can do more or less the exact same thing, just cutting the strips in the vertical direction now and defining our grid slightly differently to cover edges A1, A2, A3, and B3. So this is what the bilayer construction looks like. This is the graph on each side is going to look like a bunch of wheels.
Thanks. This is going to take us back maybe one slide, but can you remind us again how to interpret the arrows on the edges or how you got this because you have both arrows coming in and arrows going out from.
Yeah, that's a good question, and I left that implicit here. I guess when you have a bipartite graph and you want to consider an adjacency matrix of that bipartite graph, then you need to sort of decide which vertices are going to be my columns and which vertices are going to be my rows. So that's what this directionality indicates. And one way of, I guess what this arrow means in this situation is that these X vertices are going to be the rows and that these data vertices are going to be the columns. And that's the same convention over here.
I see. Because let's see, so the columns are, the columns of your H matrices are just the L and R bits, and the rows are basically, well, either the red or the green. Okay, gotcha.
So that explains these diagrams, but it doesn't explain this. Let's perhaps go to this slide here. Here I have a particular matrix that is labeling these different edges. And the way that this maybe can be seen might be less from the matrix perspective, but more from the group theory perspective. We could mark one of these positions on the torus by the identity element in this bicyclic group. And that lets us, by multiplication by elements within this group, essentially label all of the vertices on the torus via group elements.
Mm-hmm.
And then in order to do this walk, I'm essentially telling you start at the identity, say, and then walk according to these group elements to define this new lattice now.
Gotcha. Yeah. Okay. Nice. My memory's fading a little bit here, but this now that you say it as this bicycle, you have this outer ring and this inner ring with edges going from the inner ring to the outer ring. And you can think of some generators going between the two. It reminds me a lot of like a subgraph. I think it's a subgraph of the full poly group, like on a single qubit, for instance. Maybe that's very related, but yeah, I'll leave that there. Okay. Good. Thank you, Patrick.
Of course. Yeah, I mean, now that we have drawn the two layers, we still might be a little bit disappointed because with the surface code we were able to just draw the whole thing. Wouldn't it be nice if we were able to draw just the whole 144 qubit code in its full glory? And we're gonna try. It's less pedagogical than I'd like it to be. So what we're going to do is we're going to take one of these grids here, and this grid covers edges B1, B2, A1, A2. And that leaves edges A3 and B3. And those edges are sort of going to be long-range wires within this torus. So one way of understanding this code's graph is you just take a regular old toric code and you add a bunch of long-range wires that also have this toroidal translational symmetry. So by doing that, we will get the most eye-watering figure in the talk. So again, we have this grid here on a torus. These thick lines with the arrows indicate that, this bottom line is equal to this top line. So when we go off here, we loop back on ourselves. That's the way of drawing a torus. And then in addition to all these nearest neighbor edges that we had, we also have these long-range edges. So this is, I think, a convenient way of thinking about the code. Note that it's not the way that you'd want to build the code, because in particular, we have edges crossing here that shouldn't. So the way that it'll actually look on hardware is probably going to be different. We're still thinking about how exactly a hardware layout would go. But certainly, if your goal is just a visualization of the whole graph as a whole, it would probably look something like this. This grid on a torus plus long-range edges. Okay, so that concludes our detour into how do we actually build this code? How are all the qubits connected together? For the rest of the talk, let's talk about syndrome measurement and logical gates.
Unless you get there was a question. So if you go back a slide, just to clarify, so you're showing us only an example of a few of these, right? There will be many more.
That's right. Yeah, I guess that's what these shaded edges are supposed to indicate. That this loop here of long-range edges, this is present on all of the qubits.
It's present on all.
You just translate the same set of connections across the entire torus.
Got it. So it's basically 2 extra wires per qubit.
Right. So that means the total degree of each qubit is 6, as promised.
Perfect. And is the range, is the distance of the wires, the length of the wires bounded?
Right. So this goes into hardware implementation. How would you actually lay this graph out in real hardware? Certainly, we can build long-range wires using C couplers, but those are certainly going to have lower quality than just regular old connections between qubits. So this becomes like a game now of like how many long-range edges can we afford? Where do we put them exactly? And there's multiple different ways you could do this. Certainly one way you could try to do this is to have a bunch of long-range connections from this qubit to this qubit. So lay them out on the grid the way I have specified here, and then add long-range connections to tie these edges together near the ends, and then also have long-range connections in between here. So the disadvantage of that approach, I guess, would be that this length here would be order of, I guess, m, which is 12. In this coordinate system. So maybe there are ways of making the wire lengths shorter than that with other trade-offs. I think it's an interesting question. I don't think we've solved it conclusively yet.
And theoretically, let's say if you, maybe as you go to larger and larger, so to say, graphs, would it be impossible to say that each qubit only needs a maximum jump of, let's say, 10 or 20 or something? It doesn't scale to where I need to have at least one qubit that has this, enormous half grid jump.
Right. I think you're asking a really interesting question. So you could imagine this code as part of like an infinite family of codes that just goes to bigger and bigger toruses. Mm-hmm. And maybe you could hope that these connections, these long-range wires here, are still sort of stay kind of close. But I don't expect this to happen.
Okay.
The reason is because of a bound proved by Bravi-Poulin and Terahall back, I think, in 2009, that shows that any error correction code that has just sort of local connectivity on some kind of sheet is going to do basically as well as a surface code. And here we're doing significantly better than the surface code, so it means that these long-range wires must be doing some kind of work. So I expect that as we scale these codes to be bigger, these wire lengths are also going to scale with that dimension.
Okay, that's very interesting. Thank you. A couple of questions popping up in the chat here. So from Ron, if you wrap this graph into an actual toroidal grid, I guess going back to the torus, right. You kind of brought us from the torus here, but now let's go back. Right. After taking this on the torus, what does it look like on the torus? Do the curved lines then become straight?
Oh, these curves here?
Yeah,
You
I
mean?
think so. Yeah.
So I mean, I guess you could straighten them out if you wanted to. I have a different figure where this just goes straight out and then goes over, just sort of a taxi cab walk. The challenge is to sort of make all of the black lines only go over dotted lines, right? Because the dotted lines correspond to these wheels, and the solid lines correspond to the other wheel. So you can have solid lines and dotted lines cross, but you can't have solid lines and solid lines cross, for example.
Yeah. So maybe that answers
doing that while keeping everything straight is really tricky, and that's why I'm sort of cautioning to view this figure as the end all be all with this code.
I see. So maybe that's answering Ron's question to some degree. In 3D, if you put this in 3D on a torus, and you're saying that you wouldn't have this crossing, this sort of all live on the surface of this torus.
Certainly for the main grid, yes.
For the main grid, yeah. And the black wires are within, I guess, the inner or outer, so to speak.
Yeah, I guess you could ask this question of like, is it possible to build this in a bilayer architecture on a torus? I haven't thought about that at all. That sounds interesting.
Great. And maybe one quick question here from Blackstar Cami, since you mentioned you did a lot of this early on computer searching across once you found the original theory code. Can we use machine learning or AI to just figure out the best paths, routing, or embeddings, and so on here? What can machine learning do?
Very interesting question. Yeah, we hadn't considered that at all. So the searches that we have use just entirely traditional techniques. But yeah, trying to use AI to find particularly nice choices for those polynomials, or alternatively using some kind of machine learning to do layout of this on physical chips, unexplored. Sounds interesting.
All right. Thank you, Patrick.
Cool. So let's move on to the syndrome measurement circuit. There isn't too much to cover here. I mean, it's a very interesting construction because it relies entirely on the structure of the codes in terms of being a sum of these 6 different permutations. So what's very nice is that the X and L qubits, they're connected by an A edge, and the R and Z qubits are connected by this A matrix as well. So we can sort of run the CNOTs that are defined by those matrices in parallel. And that's essentially the property that this circuit construction exploits, is that we have a bunch of different circuit layers, each one of which covers a different family of permutations within this code in a way that's highly parallelizable. Now, it's important to note here that it doesn't suffice to just cover all the CNOTs. You need to do this in a way that makes the stabilizer gate computed by this circuit actually map the correct stabilizers to the right spot. And in particular, if we were to put this A1 CNOT over here with this A3 one, as you might be tempted to do, that doesn't work. So there was some amount of optimization involved in trying to figure out exactly how do we position these different edges to make this thing actually compute the right thing. But suppose you do, then you have this very nice property that this is just depth 7, so constant in the code parameters. And even though we have one circuit starting earlier than the other, they can still sort of slot together into one another. So you can just run the circuit over and over. So that's a nice property of the syndrome measurement circuit. Perhaps a property that's not so nice is that it's not distance preserving. So what does that mean? The distance of an error correction code is sort of the minimum number of errors at any point that could cause a logical error, that could cause an error that you can't detect that changes the logical information. So for the 144 qubit code, the distance was 12. However, if you apply, say, maybe half of these CNOT gates, or worse, have errors just in the wrong spot, then you can cause the syndrome measurement circuit to introduce logical errors using just weight 10 errors. So the circuit level distance, as it's called, can be a little bit lower with the circuit. However, the experiments that we showed demonstrate that even with this reduced circuit level distance, we're still very competitive with the surface code.
Thank you, Patrick. I think you're hitting on 2 things here from Sedan. But maybe before we get to the fault-tolerant question, can you just explain for us when you write the measurement box with X, do you mean parallel single qubit X measurements? What exactly does the box mean?
Yeah, that's an excellent question. So here, I mean, I have just 6 plus states, but the reality is, of course, that there are, well, for the 144 qubit code, 72 many X checks. So as we mentioned before, we have this set of X checks and the set of L checks, and they're connected via this bipartite graph. This bipartite graph's adjacency matrix is the sum of 3 permutations. Here we're just considering this A2 permutation, say. We talked before, like if you have a bipartite graph and a adjacency matrix that's a permutation, that's just going to pair the qubits up. So what we're saying here is just consider that set of pairs and run CNOTs on all of them in parallel.
And the very final measurement box, those are individual measurements on each qubit.
That's right, yes. So measuring all of the check qubits in the Z basis or the X basis. That's going to tell us the data that we're then going to use to correct the errors.
Got it. And I think you kind of touched on this, but a question from Sidant about fault tolerance and propagation of errors in the circuit. You mentioned you ran some kind of experiments that, I guess, numerical experiments that looked at the effect of errors which are non-fault tolerant in here and how they affect the effective distance. And you're saying basically, it's a bit of an issue, but it's not that big a deal. Is that roughly the message here?
Yeah, that's right. So in order to, so what we did is we computed the circuit level distance using some simulations that try to place errors at different locations in the circuit and see how badly they propagate. So there's a bit of a combinatorial explosion here. So these simulations are a little expensive, but we were at least able to give good bounds on the circuit level distance for the codes for the smaller codes.
And what is the effect? Maybe quick take here. What is the effect of biased readout errors? So I guess in these simulations you're doing Pauli errors, which are, they're biased in one sense, but when you have readout errors, you can have sort of a more probability that you get 0 than you get 1 flip. So it's biased in a different way. Does that have a very detrimental effect, or does it kind of play out in the same way as the rest of your simulations?
Right. So the circuit level noise model that we considered is a simplification of what's happening on the hardware, or even a simplification of more reasonable and tractable noise models that we have of our hardware at IBM. So I think it's a really interesting question to consider. Well, in simulation, how well would we expect the circuit to perform with a slightly more intelligent noise model, with a noise model that leverages our understanding of the hardware a bit better? Again, a really interesting open question. I expect that doing this will improve performance. And the reason is that there is a fair amount of literature on these sort of biased error, quantum error correction techniques, like say where a Z error is more likely than an X error or something like that. In situations like this, it's shown that you can dramatically improve the performance of codes if you know that the noise is biased in a certain way. Whether or not that's going to take place here, we still need to check, but my gut feeling says it'll help.
All right. Thank you, Patrick.
So finally, maybe in the last 10 minutes, let's talk a little bit about logical gates and load store operations. So the goal here is to read data in and out of the code such that we can actually do something with it. So in order to do that, we need to locate our logical qubits within the code. What do they look like? And the way that that's usually done is by finding representations of the logical Pauli operators. So a particular logical qubit might have an X operator on it or a Z operator on it. And to some extent, we can sort of work in the Heisenberg picture, not really think about the actual qubit itself, but just think about this X and Z operator that corresponds to this logical qubit. So let's try to see what these X and Z operators might look like. So I'm going to be doing a bunch of analogies to the toric code here. In some ways, there are some similarities, and in some ways, there's some differences. I think that's going to help us understand what these logical Pauli operators look like. So in one sense, we, of course, have the similarity to the toric code, is that a very nice way of picturing this code is via a grid on a torus, just like the toric code. So that's a similarity. A difference is that in the toric code, the logical operators correspond to these topologically non-trivial loops. So we could have like a chain of Z's that are like vertical here. Uh-oh. That's a fire alarm.
And hopefully
Yeah.
that's all it's there. Safety first.
Safety
I don't hear
first.
it anymore.
So the way this building works is that we occasionally get a fire alarm that's just for one floor, or sometimes it's the whole building. And which one it is they're going to tell us at the end of this message. Let me open the door. Sorry about this, folks.
No worries. Don't worry, Patrick. I think the last thing we want to see is big fire behind you as you're trying to finish your talk. So no, we are not going to make you do that.
Yeah, safety first for sure.
And don't worry, I think some of the folks here in the seminar are really finding this quite fun, especially, we got some good puns. Give us your best fire and quantum pun. I see Neximus has quantum on fire right now, guys.
Mm-hmm. Yeah, I'm really excited about this result. Perhaps regardless of how it pans out, maybe it would be responsible just to stop now. So thank you all for listening. I thank you for all of your questions. Maybe I can hop on after all of this to answer some questions in the chat. Do you think that might make sense?
If we can keep the chat alive, I don't know, that the video producer, Paul, here will know if that's possible. I think Paul is telling me that.
Hey, everybody. The chat will go down after we stop, but the comment section below the video will stay up. So, Patrick, if you want to post there, you can, or if people want to ask questions in the comments.
Sure, absolutely. Let's do that.
Yeah. Thank you, Paul. Patrick, let us know that you're safe, and sure. We'll keep everybody posted. And yeah, be safe and have a nice weekend. I think everybody's saying great talk. I think we got the message. This is exciting, and you should probably go run outside and take precautions. So thank you so much, Patrick. This was wonderful. Thank you.
Thank you, Zlatko. Thank you, everyone.
Yeah. We'll answer questions in the chat.